What I have here are several different PLCs that are mounted to a trainer board. You got different models, different types, different manufacturers. This one right here in the front, the rack system, is an Allen Bradley rack system, an SLC 500. You have a power supply right here, which is a P2 power supply. There's a CPU in the first slot. Then we have an input card and two output cards. Notice the lights. These lights tell me which inputs are currently closed, and the outputs, when we use it, will tell us which outputs would be currently on. Now, the rack systems are typically used for larger areas, multiple equipment, larger systems. So I can hook up multiple equipment and run multiple equipment through one PLC. Now, these little brick processors, Direct Logix 105, Allen Bradley, Micrologix 1500, these are basically small bricks. What they're going to run is typically individual equipment and small processes where you don't have the need for multiple or lots of inputs and outputs. Now, one of the similarities these PLCs have is right down here in this little key switch that I'm pointing at here. This key switch can operate in 3 modes, and it controls the mode of the processor. If I put the switch in one mode, this becomes program, and all the PLC will do is program. If I put the switch in the other side, all it'll do is run. So you can't tweak it, you can't do anything with it other than run. Now, most of the PLCs are going to be in the position called RAM. This stands for remote. It's remote program, remote run. Now the mode of operation is based on the software inside of the CPU. That's the most common position these are going to be in, because I can program and run right here. Now, over here on this Allen Bradley 1500, this little dot right here, it's a little toggle switch. If it's up, it's going to be in program mode. If it's down, it's in run mode. And if it's straight up and down in the center, which it is now, it's in RAM, remote program. Now, the Direct Logix doesn't have all those fancy features. It's only got one mode, and that's going to be RAM. So everything we do with this is based on the softwares. So PLCs, now we got different types, we got different manufacturers, we got a little bit of similarities in here. We can actually even add to that this guy, a Mitsubishi. Again, this one is only going to have one mode, and it's going to be in RAM. But this is a little bit different PLC, even though it's a different color, shape, and a size. These 3 are workhorses in the industry. This one gets into higher speed processing. But not every application requires high-speed applications and high-speed processing. We're going to get into that in later videos. Now, one of the biggest differences in the PLCs isn't just the shape, the size, and the color. Internally in the PLC right there has to be programmed. And this is where the biggest difference is. Every manufacturer has to have their own softwares. It's all proprietary in every piece. So for every individual make and model PLC, you typically need different softwares. That's where the problems start to exist. We are going to look at the different types of softwares that are used for the different PLCs. Well, the similarities are going to be the similarities. Now, first of all, every one of these guys are going to have some type of file system which is going to be different for every make and manufacturer. Every one of these are going to have toolbars. Standard Windows toolbar on the top, function toolbars below it. Well, the toolbars, function toolbars are going to be different with every software. But one of the similarities they have is they're all going to have the same exact type of programming. Right here, what I have here is relay ladder logic. One side right here is a power rail or a logic rail, and the other side is the return. So in other words, I'm going to actually turn on different outputs. These numbers right here are numbered for my input card, slot number 1, screw terminal number 3. So there's always going to be a numbering system as to where the input terminal is. What's connected to that input terminal could be virtually anything. Push buttons, selector switches, proxies, you name it. Now over here is going to be my outputs. I have output card, slot number 2, screw terminal number 6. Right here I have identified what the output actually is. Right here I have identified what the input actually is. Well, this simple software right there is going to operate what's called a counter. It's going to be a count up counter. Now I have this counter preset to count the number 6. The accumulator right now is currently sitting at the number 1. And what I have this is my push button number 4. So if I come over here and push my push button number 4, when that push button closes, this counter's accumulator goes up by 1, turning on the output. This little device here is going to open the contact right there and shut the output off. But now this statement right here is a comparison. Greater than or equal to. I'm going to compare the accumulator of this counter. So this accumulator is right here. I'm comparing it against the number 2. When that accumulator is greater than or equal to the number 2, the output turns on. Now if I go down 1, here we got another comparison, greater than or equal to. We're going to compare the counter's accumulator against the number 3. When this accumulator, which is currently at the number 2, reaches the number 3, the output turns on. And all I have to do for that is push the button. The output turns on. Now let me scroll down here a little bit. We even got more. We have another greater than or equal to statement. Source A is the counter's accumulator, which is currently the number 3. This compares against the number 4. So when that accumulator reaches the number 4, becomes greater than or equal, this output turns on. And again, all I have to do is push the button to do that. The output turns on. Now down here we have another one, greater than or equal to. This is going to be source A is the counter's accumulator. It is currently the number 4. When it reaches the number 5, this output turns on, which is a binary. It's a virtual relay. So this binary turns on. The address right here is the same address as all these others. So when that happens right there, this turns on, these contacts open. But now this time-based contact right there is part of a status file. This status file is operating addressed to the CPU time clock. So now this is set to operate about every half second. So this is going to cause the lights to blink. And all I have to do again is push the button once. And everything blinks. So ladder logic, it's not exactly difficult. This is more of a complex program to work with. It's only going to be several lines, but everything operates several lines. Now the last line right here is going to be what's called a reset. Okay, now when this counter right there, C50, reaches its limit of 6, it's going to reset the counter back to 0. So now we go ahead back up here, there's the preset 6, the accumulator's 5. I push the button again, it goes to 6. But now there's a problem. When I push this button, it goes to 1. And it goes to 1 because I'm not fast enough with my finger. So it counts the number of scans. And the time it actually pushed the button, that CPU scanned 300-400 times. So it actually counted up to the next number. Now this one is a simple Allen Bradley programming. It's not exactly complicated. It's probably some of the easiest to use. But now let's progress on to some of the other types of PLCs and programming for them. This is just the introduction, guys. We're going to get deep into this. What I have here is another software from Automation Direct that runs the Direct Logics types of PLCs. Well, here we have a file structure on one side. We have the standard Windows toolbars on the top, and now we got all the application or the actual toolbars for operating here, but now they look a little bit different. All my programming and commands are off to the other side. So in other words, all the file structures again are different because this is a different software. But the programming portion is almost identical to the others. Simple ladder logic. So what I have here is a simple 6 rungs of the ladder, 7 with the end statement. Right here, this stop button is referring to an X. So X10. So this is my screw terminal, X10 on the PLC. That's a stop button. My run button is going to be connected to terminal X number 2. I have a reset button, and I have a timer accumulator. This is a counter. Counter 0, it's going to count to 5. Now here we have a different set of comparisons. Okay, when counter accumulator 0 becomes greater than or equal to 1, the output turns on. Counter accumulator 0 becomes greater than or equal to 2, the output's on. And it counts to 3, counts to 4, and finally it resets. Now, how do we know whether or not the program's working or not? Just like every program, when we run the program, it's going to show the status of the program as highlighted. So every one of these become highlighted. When this contact is highlighted, it's activated. When this contact is not highlighted, it is deactivated. Later on, we get into this terminology, and this would be a 1, and this would be a 0. So we're going to talk in terms of binary language, which is much easier to describe every one of these. I'll get more into that quite in depth. Now, it's very simple. I come over here, I'm looking at button X2, so I push my button X2. Right there it highlights. I got a little bit of a lag. I let go of the button, and my output turns on. On my trainer board, my light's on. I push the button again. Well, we went up to the number 2 on the counter. The output turns on. I push the button again, and the counter goes to the number 3, and the output turns on. We have 4. The output turns on. Okay, we push the button again, it resets. PLCs don't have to be that complicated when we work with these things. The programming makes it very easy to actually troubleshoot the PLC. These are the inputs. Okay, the input is going to turn on the outputs. If this output doesn't go on, whatever's in front of it is where the problem is. So it makes it very simple to troubleshoot mechanical equipment, okay, large systems and so forth by using PLCs. By using the highlighted numbers and contacts, this tells me which types of inputs are going to be activated and which outputs should be activated. If one of these outputs do not activate, the problem is right on this line directly in front of it. So using a PLC makes things a heck of a lot easier to troubleshoot equipment, large equipment, complex systems, and even simple systems. But you need to have access to the programming to see what the heck's going on. So a simplified in troubleshooting. Every PLC does that. Now let's look at another type of PLC program. Again, we have another software. This is what's called MelSoft GX Developer. This is the Mitsubishi type softwares. Over here on the left, we have a file system. Again, a little bit different than the others. We have the standards Windows toolbar on the top. And now we have all the different types of commands in a different format. The only thing that's actually going to be common with all the different softwares, no matter which brand or make it is going to be right down here. This is going to be the ladder logic. The programming logic is going to be the same in just about every one of these. There's a lot too in the programming. Now I don't have this one hooked up as of yet. We're going to go through this later in an individual demo. But right over here we have the same concept. X2 is a stop push button. Normally closed button in the field activates the open contact. X1 is my start button. I push the start button once, it activates a counter. This counter is going to count up to the number 6. Now our commands are a little bit different. Here I have a bracket, and this says greater than or equal, counter 0, greater than or equal to the number 1. Okay, once that counter reaches the number 1, the output turns on. Greater than or equal to number 2, the output turns on. Greater than or equal to number 3, 4, 5. But now down here, when the counter reaches the number 6, it resets the counter. Down here on this one, right here, when it becomes greater than or equal to number 5, it activates a binary, which opens these two lights, shuts these two outputs off. Okay, so the programming is going to be very similar in every one of the PLCs. It doesn't matter whose make, whose model it is. It's all going to be very similar programming regardless who did it. As we start working through some of these PLCs, right here, down here on this Allen Bradley, I have my inputs, I have my outputs, and right up here I have a set of lights. When I push the button right there, notice the input light changed momentarily, the output light turned on, indicator light turned on up here. I push the button again, the next light goes on, output goes on. Push the button again, my input turns on momentarily, the output turns on down here. Push the button again, we got another output on, and now the other output's blank. Now, that was a program we just looked at for the Allen Bradley. Now, right here, these LEDs indicate the condition of these outputs. So this LED tells me when the output is on, when the output is off. These are the inputs. These inputs that are closed contacts on my board. And they tell me when the input is closed and when the input is open. So by using the LEDs on the lights, this tells us the condition of whatever equipment we're working with. Now I go ahead and push that button again, it shuts everything off. Now we come over here to this button. I do the direct logics. I push the button once, the output turns on. Lights up right here on the terminal, Y0. Push the button again, the output turns on. Lights up Y1. Y2 lights up, output turns on. Y3 lights up. Push the button again, it goes off. So in other words, we use the actual lights to troubleshoot the equipment. It identifies what's working, what's not working. We can use the programming to actually troubleshoot exactly what's not working that causes the outputs to not work. So PLCs don't have to be complex. They can actually work out to be very simple.